Good evening, everyone. Wherever you're joining us from tonight, welcome to our series of presentations from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, or as we like to call it, kipac for short. And tonight, we invite you to join us to discover our universe. My name's Dan Wilkins. I'm a research scientist at kipac, and I'm the coordinator of our public talk series. And you can find out all about the talks we've got coming up for you, or you can watch any of our past talks again if you've missed them over on our website, kipac.stanford.edu/discover, or find us on YouTube, youtube.com/kipac. Well, tonight we're joined by Dr. Andrew Bradshaw from the SLAC National Accelerator Laboratory, who's going to tell us about how man-made satellites affect our view of the night sky, and what new mega constellations of satellites being planned will mean for ambitious deep surveys of the universe, including those by the Vera Rubin Observatory that we heard all about last week. Well, Andrew was born in Turkey and raised in Dallas, and he completed his undergraduate education in physics at Texas A&M. But he says he's a Californian at heart, and he moved to California, to the University of California, Davis, for his PhD, where his thesis focused on gravitational lensing and on laboratory studies of the camera for Vera Rubin Observatory's legacy survey of space and time, where he was interested in understanding how the imperfections in the camera's pixels will affect the astronomy that we're trying to do. That'll be a vital component in really getting the most out of these ambitious new observatories. Well, at the end of his PhD, he hadn't finished everything he wanted to do with the LSST camera, so he joined the team at SLAC last fall to help the team finish the construction of the camera and to optimize its performance. So we're very lucky to have Andrew here tonight to tell us about the effect these satellites will have. Now, as always, you're welcome to submit your questions to put to Andrew at the end of the talk. If you're joining us on Zoom, head down to the bottom of the screen and hit the Q&A button. You can send in your questions there. Or if you're over on YouTube, send in your questions using the chat window. But for now, over to you, Andrew.
Hello, everyone, and thank you, Dan. It's nice to see everyone. Let's see if I can get the screen sharing going. Okay, present. Full screen. Okay, is that working and visible?
It's getting there, I think.
Okay.
There we go.
All right. Great. Well, thanks everyone for being here. I hope everyone is having a good evening. Tonight, I would like to talk to you about something that the LSST project has been studying for quite some time, because it's a very important topic that's very evolving in the current times. So, the satellite streaks and surveys of the sky is the topic of the discussion tonight, and I would like to thank a lot of people for helping me with all of the work that is being presented tonight, in particular Tony Tyson, my PhD advisor, Aaron Rudman, my advisor at SLAC, and all of the LSST camera team, including in particular Homer Neal, Craig Lage, Adam Snyder, Dan Poland, and as well as the entire SatCon 1 panel, who I'll be crediting later this evening. So to start things off, we can discuss perhaps this interesting uptick in UFO sightings over the UK that was in the news last year, around last spring. And so this little animation here is actually a real-time video of the SpaceX Starlink satellite train going across the sky shortly after their launch last May. And the satellites, which you can see is this little train of dots that are flashing in brightness, are several hundred kilometers away from the camera, the handheld camera here, as you can see, and they're flaring. And by eye, you could understand why some people might think this was a UFO. Some of the people in the UK understandably thought they might be bombed, like at the moment. And so there was a lot of uncertainty around this particular time, and a lot of interest online and within the astronomical community, because the brightness of this satellite train was completely unexpected. And so worth further investigation. So minutes before that satellite train, there were 60 or so shiny satellites deployed about 300 kilometers over the North Atlantic. And here you can see a couple of the deployments of the Starlink satellites from various launches. They're launched every month or so, it seems. Every 2 weeks is the goal. And they're working up towards a huge constellation of satellites of these very shiny things that you can see being deployed. And so it's not UFOs. We know exactly what they are, but their consequences for people on the ground were kind of unexpected. So that's the focus of tonight's talk. So yeah, while this may look like an alien invasion, it's not. This is just the consequences of our ever-growing technology, and in particular, the growing presence of our technology in lower Earth orbit. These are the Starlink satellites all stacked up, ready to be deployed. So these satellites are so bright and shiny that you can actually see them from your backyard. And just last year, I was, of course, very interested in these satellite streaks and took my own camera into the backyard and set it for 10-second exposures and took a couple when I knew that these satellite streaks would be coming over. And lo and behold, here these little satellite streaks were passing through the Big Dipper, and 59 more followed this single streak over the course of about a half an hour. And you could see them by eye. They were moving quite quickly, maybe a degree per second. And so it's very striking and very unusual, something that hasn't been seen in the skies very much. And so it gathered a lot of attention. And a lot of astrophotographers in particular started looking at these. And so people with better astrophotography skills than myself pointed their cameras at the sky. And here's the Big Dipper being invaded by these Starlink satellites over the course of about half an hour. These were also shortly after launch, so they're very bright, very low to the ground, and you can see them in the sky very clearly. And so 2020, I think, amongst many other names, it will be the year of Starlink astrophotobombing. It has had a huge impact on astrophotography for amateurs and astronomers alike. On the left, you can see the comet Neowise, which graced our skies a few months ago, being invaded by Starlink satellites. That was a long exposure stacked up to kind of show the effect of long exposures on a single deep sky object. And on the right, you can see a Milky Way image, a beautiful Milky Way image with the foreground being kind of overwhelmed by these Starlink satellites. So why exactly are all of these satellites going up? Well, it's to connect the entire world. It's an incredibly important goal, I think. Around half of the world has no or very little connection to the internet. And so I think it's very important to connect the world, but we also have to be aware of the consequences of this technology. And so we were completely unaware of the consequences before they were launched. And it was only upon launch that astronomers and the public were surprised with their brightness in the sky. And so only a year has passed since those first Starlink satellites were launched, and studies are ongoing. But this is clearly only the beginning of a long-term development. And so the complexity and the magnitude of the problem are currently unknown, but they're requiring study. So how can we possibly understand that complexity and magnitude? Well, we have to approach it with observations, models, and data. So that's what we'll be talking about tonight. And here's just a short little video to illustrate the problem coming in the next decade or so. This is a video of the expected number of satellites over the Earth in low Earth orbit and a little bit beyond that over the next 10 years. And as you can see, every year or so, more and more are added by the thousands, some of them very low Earth orbit like Starlink satellites, and some of them higher up. And each of these different types of orbits will have different consequences for observers on the ground. But as you can see, it gets pretty extreme pretty quickly. We're only in the 2025s now, but already there are tens of thousands of satellites planned to be in orbit by this time. And so you can imagine the Earth being enveloped in technology and all of the consequences that come along with that, including the consequences for observational astronomy that we'll be discussing. So let me close this. Okay. So we need to study them. And one of the things that we've been able to study are these images of the satellite streaks on the sky. And so what we've learned from studying them on the sky is that these images of satellites are mostly Gaussian. They're long, straight lines, but their profile is Gaussian. It's a bell curve, as expected from the way that the atmosphere scatters the light from light sources above the atmosphere. But they also have long tails. So the long tails of the light that you can't really see in the upper right animation, but you can see in the left figure, the blue line far exceeds the Gaussian expectation of the atmosphere. And so there's scattered light that goes across the entire camera that you have to deal with as well, not just the main streak. And of course, just like stars, these satellites also twinkle. They move with the atmosphere and all of the perturbations that are hundreds of kilometers between us and the object. And so they shift in their centroid. They move in apparent position as they traverse the sky. So these satellite mega constellations will be a huge issue for surveys of the sky in particular. For astrophotographers on the ground, they will have, images ruined and things like that. They'll have to retake them, or perhaps their images will be lost entirely. But these surveys of the sky trying to complete science goals, they'll be affected as well, and they'll need to be mitigated in order to make sure that the science is acceptable and that their impacts are not too bad. And so in particular here, there are shown three figures of kind of the impact of satellite constellations on ground-based observatories. On the left is a Subaru Hyper Supreme Cam image of a satellite streak passing through one of the CCDs. And you can see that it produces a straight line that's very bright compared to the stars that are nearby. And it has a pretty fixed width, and there's a discontinuity when it crosses over between two amplifiers of two CCDs. And so it kind of reveals parts about the camera that you can use to study. And so there's something to be learned there, of course. And in the middle image is a particularly wide field image that was invaded by these Starlink satellites. This was taken by the Dark Energy camera back in 2019 in November. And a whole bunch of these Starlink satellites crossed the field of view at that time and invaded the deep sky images of stars and galaxies. And on the right, you can see a simulated projection of what about 50,000 Starlink satellites would look like once the Vera Rubin Observatory is up and running. And so these streaks that you see in the images on the left are multiplied across the sky. And just in a few minutes, you can see 1,000 or so of them across the sky. And occasionally they will go across the field of view of the camera. So this is a problem that needs a solution. And one of the ways we have been approaching this problem is to coordinate research between astronomers all over the world to get recommendations for both the operators of these satellites and the observatories that will be affected by the satellites. The main conclusions of this report are that the human experience of the night sky the effects on the human experience of the night sky will range from negligible to extreme, depending on how you're looking at the night sky. One of the largest impacts that I think will be kind of immeasurable is the loss of discovery of new phenomenon. As quoted by the New Worlds, New Horizons Decadal Survey of Astronomy and Astrophysics in 2010, astronomy is still driven by discovery. You kind of find what is new out in the sky, and you're driven, the science is driven by that. And so anything that gets in the way of that discovery or masquerades as a discovery has a potential impact on the science of our astronomy going forward. So in order to mitigate the impact of these Starlink satellites, lots of simulations were undertaken to see the impact on our skies. In particular, here is a simulation of the wintertime skies above Cerro Tololo, a Chilean observatory where a lot of astronomical telescopes will be placed. This is the effect of the sunlight scattering off of the satellites that you can see in the upper left-hand panel. A lot of satellites orbiting above the surface of the Earth, and you can see the sunrise or the sunset sweeping across the sky. And so eventually, once nighttime comes and night is dark enough, the satellites go into the shadow of the Earth and you can't see them anymore. They get dark enough that you can hardly see them at all. But the sun rises again, and then even when it's below the horizon, these satellites up in low Earth orbit are illuminated and begin impacting our observations of the sky. In summer, it is even worse. The nights are shorter and the sun is higher in the sky, and it has an even larger effect. So you can see satellites that are very bright and shown as orange dots. They completely cover the sky during the summer. And so these satellites will invade our images of stars and galaxies, and we'll need to find a way to correct for them. Here's just a static visualization of the number of starlinks above the horizon and above certain degrees above the horizon, 10 degrees and 30 degrees. And so the blue line is perhaps one thing to keep an eye on in this figure. The blue line is the number of illuminated satellites just in the sky from this particular point of view. And so as you can see, as the night goes on from left to right, time goes from left to right here, you can see sunset happens, and then the sun goes a few degrees below the horizon, then more and more, and it gets dark, and then all of the satellites finally become unilluminated, and you have a completely dark night sky as things used to be. But this problem is worse in the summer. Even once the sun sets, because these satellites are above the Earth in orbit, they can also still be illuminated during the summers. And so you will have a couple of hundred visible satellites in the sky, even at midnight during the summers. And so this is something to keep in mind. And one particular problem, we've only been discussing the Starlink satellites, but of course there are lots of potential satellite operators that are looking to provide internet and various other services. And one of them is OneWeb, a satellite company that's had troubles in the past, but is now looking to go forward with a mega constellation of their own. And one of the problems with their constellation is that instead of being at 500 kilometers above the Earth, they're at 1,200 kilometers. And so during the summer nights, there are far more satellites still illuminated during the night. And so these will be very bright and seen at all times during the night. And so they will need further study and perhaps mitigation of their brightness before launch. So the telescope operators would like to know exactly where these satellites might be so that they could perhaps dodge them. And so already there's been an app developed for this purpose, and there are simulations of satellite brightnesses from any position on Earth that will be in a particular direction in the sky at any time. And so you can use these to kind of guide your observations. But it turns out that these satellites can't actually be dodged very easily. As you can see, there's lots and lots of these satellites going across the sky. And so dodging them becomes a very large problem. But the good news that has come out of this past year or so of work is that academia and industry can collaborate. The SatCon 1 conference that was undertaken this year had participation from both industry and academia, and they were all working towards a common goal of protecting our skies. And so there was good progress made with this first inaugural satellite conference, and there was lots of discussion from both sides on how we can all work together. In particular, there were improvements over the past year to the brightness during orbit raising. So when these satellites are first launched, just a couple hundred kilometers above the Earth, they need to be raised to about 550 kilometers above the Earth. And previously, these satellites were kind of just let to fly free until they're raised in their orbit and then in station at about 550 kilometers. But after the reaction of the public and astronomers in general, they have since reconfigured their orbit raising pattern to, instead of having an open book configuration on the right, where the solar panels can reflect a lot of light down to observers below, they've now gone with a shark fin configuration where the light perhaps isn't optimal for collecting for the satellite, but it is optimal for not seeing it from the ground. And so that was a nice change that they made for ground-based people to not see their satellites. They also made a mitigation to the satellites that were launched after the first batch that were darkening particular surfaces as seen on the satellite on the right, where there were these little radio antennas shown as white patches that were darkened to allow for less light to be reflected. And so this had an impact of about a factor of 2 on the brightness, but still far too bright and still visible by eye. The largest improvement to the design of the satellites came from adding visors to the satellites, which is kind of a fun conceptual idea. It's just like the sun visor in your car, where you flip it down and it blocks the light from hitting your eyes. And in the configuration on the sky, it blocks the sunlight from hitting the very reflective surfaces of the satellite. And so the results of these modifications are still under study, but the results are looking promising for at least getting them to a darker than visible by the naked eye level. So as I was showing before, it doesn't seem like we can actually dodge all of the satellites. And so for surveys of the sky like the LSST, they will absolutely contain satellite streaks. On the right, you can see attempts to dodge these satellites when you have no satellites shown in blue. You can see the number of observations versus where the sun is on the sky, if it's far below the horizon or just below the horizon on the right. And so you can see as the number of satellites increase, the number of observations, particularly near the sun, decreases very strikingly. And the number of observations that are not impacted by satellites also decreases by a factor of 2 or so. And so these impacts are quite extreme. And particularly the near sun observations where we search for incoming near Earth objects, those impacts are particularly concerning because we would like to have an early warning of anything that might be coming in our direction. So we would like to study further these satellite streaks and their impact on the Rubin Observatory CCDs. So the camera of the Rubin Observatory is the largest digital camera ever constructed, and it's up and running and working very nicely now. But we haven't been able to see the particular impact of satellite streaks just yet. And so we are looking to simulate the effect of satellite streaks on our camera. And so there are lots of stringent scientific requirements that need to be met. In particular, the photometry, the measurement of brightness. You need to be able to measure that to extreme precision, and the shapes of objects and the transient nature of objects. All of these things are being discovered on an entirely new scale that needs to be very precisely calibrated and corrected for. And these satellite streaks are going to be a nuisance. So soon after the launch of the first batch of 60 Starlink satellites, as the Astro Twitter was exploding with new observations of these satellites flying above, we realized that this would have a large impact on our upcoming survey of the sky. So after the Memorial Day holiday, we immediately started working on simulating the effect of these satellite streaks on our CCDs. So on the bottom left, you can see our little mock-up, just a simple hemispherical 2 pieces of metal or plastic wedged together where light can go in between. And then we stick this little mask into our optical simulation of the LSST and put our camera on the other end, or one tiny piece of our camera on the other end. And then we can get all sorts of measurements and images of satellite streaks on our CCDs. In particular, there are 3 features that we observed with these first simulations of satellite streaks on our CCDs. Shown in red, pointing to the various scattered light in our camera, you can see there's a main streak that's very bright in the very center, but there is light that's scattered out very far away from that main streak. And so this scattered light needs to be removed from the images or masked out of scientific analyses before you can proceed with the survey. Also, particularly worrisome are the multiple orders of crosstalk between various amplifiers of our camera. And so our camera is segmented into thousands of channels that each are read out independently, and all of these channels are very closely packed together. And whenever you read out all of these electrons from our camera, they tend to kind of communicate with one another across signal channels. And this is called crosstalk, and it's an inevitable property of just electricity and magnetism, but it has an impact on our images. And so on the right, you can see these streaks that are pointed to in green arrows that are parallel to the main streak. These are the crosstalk streaks that happen when a satellite goes across our camera. And they're about 1,000th or 1,000,000th of the main streak, but this is still well above our signal and noise threshold in our images. So it's something that we need to consider and correct for. Also shown in blue, these horizontal black stripes was a particular feature of our CCDs that we've since corrected after discovering it in images that were simulating satellite streaks and other images that were simulating observations. So we've learned something from simulating satellite streaks as well. And hopefully we can work on the other problems that plague our CCDs with these satellite streaks. So you get a lot of data. You can get a lot of data, and in the figure on the top right are satellite streaks that were done at a variety of intensities. You don't particularly know what intensity the satellite will be when it crosses above you. It depends on the the angle between the sun and the earth, and how far away the satellite is, and how bright and reflective it is, and all of these things can vary. So we need to be prepared for all sorts of satellite streaks. But as it turns out, this crosstalk between channels depends upon the brightness of the streak. And so you kind of have to tailor a correction for this crosstalk to each streak. And so this has required a lot of study, and these studies are ongoing, and but the results so far are looking good. So on a personal note, after studying all of these satellite streaks last year, I was volunteered to help construct the LSST camera at SLAC. And so I was really happy to join the team and continue some of the studies, as well as helping to build the focal plane. And just last month, we had a wonderful press release of images from the full focal plane. And on the right, you can see our namesake for our observatory, the Vera C. Rubin Observatory, imaged by our full focal plane, 3 gigapixels of information read out by our full focal plane just recently. So that was a nice achievement. But the studies were ongoing. So I continued my Starlink satellite streak simulations on some spare sensors at SLAC, in particular using this small slit. As you can see on the far left image, you place this small slit into a specially designed camera, or a projector actually, with lenses, and measure out the distances and project it onto the camera. And so on the bottom, you can see the satellite streak projected onto the camera inside of the clean room at various different orientations. And we get lots of data from this, and we analyze it and look for interesting features that we can learn from. And so we've made streaks that go vertically and horizontally, and we study the crosstalk in particular. Can be studied in this manner. And the images that result look particularly bad, I would say. They were a bit shocking. When I first started simulating this, it came as a surprise, in the same way that the brightness of the satellites came as a surprise to everyone on the ground. The crosstalk seen in the images of satellite streaks that we simulated in the lab also came as a surprise. And so this grid of lines intersecting and crisscrossing, resulting from just a simple line of light going across the CCD, was particularly worrisome. And so, but this is part of the discovery process and the learning process, and we've learned a lot since then. And so you can see that just a simple algorithm that I have developed along with some other teammates can remove this web of crosstalk streaks from our images, and it just leaves the main streak of the satellite to be dealt with. But that's but I think it's a step in the right direction. And so, as I was talking about before, you have to deal with satellite streaks of various brightnesses. And so here is a satellite streak shown, simulated on our sensors for a variety of brightnesses, from very low, very bright satellites to something that's very high and very dim. And you can see that the brightness of the crosstalk streaks varies with the brightness of the image. And a preliminary correction algorithm was developed, but needed updating to make sure that all of the tiny residuals that were left over from the correction were deleted. And all that is left over is noise and the main streak of the satellite, which will then have to be masked out. So we've essentially solved the problem through modeling and data. More work is, of course, needed, but I think we're going in the right direction with all of our work being done at SLAC. And so we look forward to the next steps that we can take towards mitigating this new problem that we've got on the sky. And so all of these studies will hopefully be able to prevent a lot of the problems that will be present from these satellite constellations. Okay. That's it.
Hey, great. Well, thank you very much, Andrew, for that very interesting presentation. I mean, it's something we often don't think about, the man-made satellites that we're putting up in orbit that, of course, have had such a transformational role in our technology and in our communications, can actually impact the sky that we see and have a big impact on these observatories. So I wondered if you could say a few words for our audience just about the sort of science that the Vera Rubin Observatory is trying to do that is particularly affected by these satellites, and why we should try and protect that science.
Absolutely. Yeah, so the Vera Rubin Observatory has a very wide-ranging set of science goals that are predicted to be achieved in the 10-year survey. One in particular that I'm interested in is the shape and orientation of very distant galaxies. And so these very faint galaxies are aligned via gravitational lensing. As their light comes from us from very distant galaxies, it gets distorted by gravity, and we can study this distortion. But if we've got a set of lines that are going across the survey and we can't correct for these perfectly, we have a correlated signal that's leaking into our background galaxies. And so we are a little bit worried about some of the residuals that might be left behind by the correction algorithms that could impact the science. So the studies are still being, they're still ongoing for that particular subject. But of course, I think the main thing, we can't actually estimate the impact of these satellites on our science. In particular, the loss of discovery. You know, there will be things that go bump in the night that will be discovered by the LSST, and if that bump happens under a satellite, then that discovery is lost and it's irretrievable. And so the consequences are inestimable for a lot of these things. So we're just beginning to learn about the impact of these satellites on our science. And
yeah, sure. And of course, gravitational lensing is one of the best ways we have of understanding where everything is in our universe and how our universe is expanding, how our universe came to be really in the state that we see it, how we can go from the Big Bang to the universe we see today. So it really is important in understanding where we came from. And I completely agree with you. It's with these big observatories, there's all this science we know we're going to do, but there's all these things, as you said, that go bump in the night. All these discoveries that we weren't expecting, and anything that gets in the way of our telescope could either pretend to be one of these new discoveries, or it could get in the way of one of these new discoveries.
That's right. Yep. So we need to start now to work on the correction and the mitigation of all of these things before it really becomes a problem in just a few years.
Sure. So how were we handling the light from the satellites before Starlink was launched? Is there something about Starlink that means it's going to have a much worse impact on astronomy than all of the sort of communications and imaging and other satellites that we already have in orbit?
Mm-hmm. Mm-hmm. Yeah, so I mean, satellites have been around for over 50 years now. And I think maybe perhaps some of our audience knows about various flashes from radio satellites that you could see, these so-called iridium flares. Some of these you could see during the daytime, they were so bright. And so you could go out, and if you had the time and the location right, you could see a flash in the daytime sky of a satellite during its orbit over you. And so they've been around for quite some time, but what's really changing now are the numbers, and the numbers of them that are close to the ground and very shiny as well. And so it's previously it was just kind of you forget about it, you almost sweep it under the rug.
Yeah.
But now it's an issue that you can't ignore. With several of these passing through each exposure that the Rubin Observatory will take, you need to be able to understand them to an extreme precision now. With all of the data that's collected, you need to be able to weed these out to very fine precision so that you can be sure of the results that come out of the survey. And so it's really more about the numbers now than about any particular difference in the satellites or the way that we're handling the light. It's just about precision now.
Yeah, so I guess in the past you could dodge it, or if you happened to take an image that had a satellite streak going through it, you could throw that image away and get another one. But now with so many and having them so much closer to Earth, so they're more reflective and we're seeing more of their light, it means anytime we try and retake that image, we're going to see the satellite going through it.
Yep. You can't dodge them. Eventually, you won't be able to dodge them. You just have to live with them. So.
Yeah. And is that something that's sort of changed with the way we're doing astronomy? So with the Vera Rubin Observatory, we're doing this survey where we're scanning the entire sky, or at least the entire southern hemisphere sky that it can see, instead of just looking at individual objects. Is this surveying more susceptible to the satellites?
Absolutely. Yes. The survey is driven by the science requirements themselves. And so it's particularly susceptible to anything that can interrupt those survey goals. And so, as I mentioned earlier, one of the science goals of the LSST survey is to catalog all of the asteroids in near Earth orbits, and in particular identify threatening asteroids. And a lot of these searches happen during the twilight hours when the sun is just barely below the horizon, but these satellites are very bright. And so this search for near Earth objects is particularly impacted by satellites. And that's a worrisome consequence. And that's something that I think we need to be aware of and be prepared for as well.
The last thing we want if we're trying to identify threatening asteroids is a satellite that either gets in the way or looks like an asteroid or or anything like that.
Yeah.
So talking about these ways you and your colleagues have come up with to mitigate the effects of these satellites, you're able to get rid of that crosstalk. So those ghosts, if you like, of the streak that just when the electronics end up talking to themselves. So the image from one pixel ends up appearing in other pixels. But what about the actual primary streak? Is there a lot you can do about that with post-processing?
If it were a perfect situation, I think that we could perfectly model it out and we wouldn't have to worry about it so much. But the problem is that these satellites they've got little bumps and features on their surfaces. And so as they're crossing over, it's not a constant brightness, that it's twinkling. And so that really complicates our ability to model out their effect or subtract all of the light from that satellite. You really have to know a little bit more about the satellite, which there are studies ongoing to kind of model these satellites in the way that they reflect light. So, we're just at the beginning of studying these satellites, but it may be possible that with a combination of information about the satellite and observations on the ground, that you could actually model out that light. But the default assumption right now going forward with the pixel processing of, all of the entire gigantic database of the Vera Rubin Observatory survey is that it's just going to be deleted. It's going to be lost area. And so that's a small fraction, maybe 1% or more, depending on how large these satellite constellations grow. But that's a percent or more of a 10-year survey. And so a lot of this lost science will have to be made up with extra time or extra observations or extra effort in development of algorithms and studies. And so there's a lot that is yet to be learned.
So is it possible to work with the companies launching these satellites in ways that maybe they could launch the satellites into orbits that avoid parts of Earth where we have a lot of observatories? Or could we paint a satellite black so maybe it doesn't reflect so much? Are these things that are being explored, or are they possible?
They absolutely are. Yes. I mean, one of the main goals for these satellite companies is to provide internet across the entire Earth, but maybe they can be reoriented as they pass over observatories, or maybe they can be darkened before they're launched. And so part of the collaboration that we had with SpaceX was going towards darkening them before they're even launched, and that resulted in some positive outcomes, absolutely. And so that's a really positive thing that's come out of this, I think, is that we can work together to protect our skies. Everybody's interested in learning about the universe and things like that, and so it's a shared goal, and I think we can all work together to make sure that they're dark before they're even launched, and that we all get the resources that we need to deal with this thing that, you know, it's providing a very good service to the Earth. I think it's a positive thing, but we also need to deal with the side effects as well. So we can do it, I believe.
So if the Vera Rubin Observatory is going to lose some of its capability potentially to detect near-Earth objects, would this increase the chances of us tracking maybe space-based missions for tracking the satellites? Is this something you could do with a space-based mission, or would that space-based mission still lack some of the capability that the Rubin Observatory has for the asteroid tracking?
Yeah, I mean, there's so many ways to go about observing the sky. One of the easiest and one of the cheapest ways to do it is to do it from the ground, because you don't have to launch anything at all. But getting to space is getting cheaper, and so one of the things that Elon Musk suggested in the midst of all of this crisis on the sky was like, hey, you know, I'll just launch the Rubin Observatory camera for you. And it's like, well, okay, it's a little more complicated than that. Of course, he knows that, but he's willing to understand what's happening on the ground, and, you know, maybe provide a way forward with all of these things that are being launched into orbit. Yeah, why not put some telescopes in orbit to help mitigate the effect of things on the ground? You can do a lot of things from a lot of things from just above our atmosphere, and you know, some of these orbiting satellites will also be affected by other satellites that are even at higher orbits. So you're not necessarily getting away from the issue at all, but you can certainly go in the right direction. And I think one of the things we've learned is that our partners in industry are willing to work together and go in the right direction. So
yeah, that's really great. I mean, I think it's one thing that's really worth emphasizing is that we'll never be able to replace all of the capabilities of ground-based telescopes with telescopes in space. And one of the things that makes the Vera Rubin Observatory special, and a lot of the other telescopes on the ground, is they are just really big mirrors. And we need really big mirrors for collecting enough light from really distant galaxies and really faint objects in our universe. And as someone who spends a lot of my job thinking about launching satellites for astronomy, I can tell you, one thing that we always do worry about is the weight of the satellites. If your satellite gets too heavy, the launch cost just goes up and up. And if you make it too heavy, then you'll just never get it off the ground at all. So I think being able to launch an 8 or 10 meter glass solid pristine mirror is a long way beyond what we're capable of at the moment, and something that we'll never be able to replace a telescope on the ground with.
That's right. Yeah, I think, you know, there might be some way to, in the long term, launch everything, but for now we're going to have to live with these things above us.
Yeah. And so moving on a little bit to the camera you're working on. How similar is the CCD camera for the Rubin Observatory to a camera that you might find in your cell phone?
I mean, at the base level, with electronics hooked up to pixels, it's pretty similar. It's all about light getting converted in a thin wafer of silicon, and that light gets converted into electrons, and you have to read out those electrons somehow. For the Rubin Observatory, the camera elements are all read out by a single readout amplifier, and that means that single amplifier can be very precise and very have a very high signal to noise measurement of each pixel. And so that's what's being used in the Rubin Observatory. What you have in your pocket, each pixel has its own readout, and that means it's much smaller and it's much noisier. And so you have a noisier image, but you can still see the sky. But these two things are very complementary. I would say, actually, there's developments in all directions with these methods of imaging the sky, and so all of them are extremely interesting, and all of them are impacted by these satellite streaks.
Sure. So I think we've just got time for one more question before we wrap up.
Sure.
So thinking about the next 10 years or so, what discovery would you say you're most looking forward to in astronomy or astrophysics?
Ooh, what a good question. What am I most looking forward to? I think that the scale in terms of depth and width on the sky of the LSST survey is something I'm really looking forward to. I think that in particular the width is very interesting to me. And so looking at the way that the structure of the sky and the very deep sky, how structures can extend across billions of light years, is very interesting to me. And the precision that will be allowed by the survey of the Vera Rubin Observatory will allow us to kind of study these extremely large structures in unprecedented detail. So that's what I'm really looking forward to the most, is the scale of the observations.
Yeah, it's just mind-boggling, really, isn't it? Just how much bigger the Rubin Observatory's observations are going to be than anything that's come before it. So yeah, I totally agree. There's a lot to look forward to there.
So exciting.
Well, thank you so much, Andrew, for that really interesting talk about the effects of satellites on astronomy. If you want to watch that talk or any of our talks again, you can find them all over on our website, kipac.stanford.edu/discover, or over on our YouTube channel, youtube.com/kipac. And you can find talks there on subjects all across astronomy, from exoplanets around other stars, through to galaxies, black holes, dark matter, dark energy, cosmic rays, and we've got much more coming up. Also, if you head over to our website, you can sign up to our mailing list so you can keep up to date with what's going on. But for now, we'll see you again in 2 weeks' time with our next presentation. Wherever you are, stay safe out there. We'll see you in 2 weeks. Bye-bye.